Hey, it's Mr. Allred, and I want to talk about the direct comparison test for series. Sometimes it's just called the comparison test. Now, there is something called the limit comparison test, and it's usually labeled that way a little bit later on. So be aware of that and try not to confuse them, because if you do a Google search, you'll probably get a mixture of both. But basically what the comparison test does is it lets us take a series that we don't know what's going on with and compare it to something that we do know. So basically, if I made up a series, I might be able to compare it to a p-series or a geometric series or something that I could prove with the integral test and then come to a conclusion based off of whether or not the other one converges or diverges. So let's kind of run through the rule here. A is the series in question that we're trying to figure out if it converges or diverges. So what we're going to do is, if we think A converges, but maybe it's complicated, maybe we can't integrate it, or maybe it's just kind of wordy so that it's hard to take the limit of, we could come over here and we could find something a little bit simpler that we can kind of test out. Maybe we'll call it B. And if we know B converges, okay, the B series converges, and we can show that every term in A, index to index, A sub 1 is less than B sub 1, A sub 2 is less than B sub 2. If we can show that every term in A is less than every term in B, then we get to say that A converges. And the reason is, remember that when we said B converged, that means if we add them all up, we get an upper bound. Well, if all the items in A are smaller than the items in B, they also have an upper bound. We don't know what that bound is. That's not what the test proves to us. It just tells us that it converges. So similar over here, if we think A diverges, we might pick a B that we think diverges, that we can prove. And if we can show that every term in A is bigger than every term in B, okay, A sub 1 is bigger than B sub 1, A sub 2 is bigger than B sub 2, then we'd know that A diverges. Okay, and that's because B did not have a bound on the summation, and the terms in A are larger than the terms in B, so it can't have a bound on the summation either. This test can turn out to be inconclusive. So if you pick something on the wrong side here, for instance, if you pick a B that converges, and then it actually turns out that your A is bigger than B, then that proves nothing. Because while B might be small enough to have a bound, if A is bigger, we don't know if it has a bound or not. It could be just a little bit bigger and still converge, or it could be a lot bigger and diverge. And all we're showing is which side of that it would be on. Okay, so this is a test that can come out inconclusive, depending on what you pick. So let's go through a quick example here, or actually two. So we're trying to determine if 1 over 2 plus 3 to the n converges. Now, that's a little bit different than anything we've done. But if we threw that 2 away, we could actually say it looks a lot like a geometric series. 1/3 to the n, where the r in the geometric series, the ratio is 1/3. And in that case, it's less than 1, so the geometric series converges. So we could show that 1 over 3 to the n converges as a geometric series. And if we put these side by side, the 1 over 2 plus 3 to the n, we can say it's smaller than 1 over 3 to the n. Why? Well, if we look at these, they both have the same numerator. The denominator of A is larger than the denominator of B. And if the denominator is bigger, then the quotient is smaller. Okay, so A is actually smaller than B. You could also cross multiply. You would get 3 to the n is less than 3 to the n plus 2. So that plus 2 would actually make that bigger. So it still holds. So we can say that because B, which was the geometric series 1 over 3 to the n, converged, and our series is smaller, that our series converges. Okay, this one's written a little weird, but what we're really trying to show in this one is that 1 over n to the 5th plus 4 times n to the third. We're trying to show whether or not it converges or diverges. And the 1 over n to the fifth is the main thing here. That looks like a p-series, where the p is 5. So if you throw this other part away, it looks like a simple p-series that would converge. So 1 over n to the fifth is a convergent p-series. And then if you take the series that we're actually got in question here, it has a bigger denominator. So that means the quotient is smaller. So maybe not every term, line by line, but eventually the terms of 1 over n to the fifth plus 4 times n to the third are less than 1 over n to the fifth. So that forces our series in question to converge. Now they do throw out an extra example here. If we still want to compare it to this p-series of 1 over n to the fifth, if we change that to a subtraction in the bottom, 1 over n to the fifth minus 4 n to the, n cubed, it is not actually less than the p-series that we're comparing it to. If you were to look at this, basically the way this is written, the denominator on the left is smaller than the one on the right. Smaller denominator means larger quotient. So as far as this inequality, they should be switched. So we don't know how much bigger our series is than the p-series. So we don't know if it converges or not. We know the p-series converges, but we don't know anything bigger converges. That's not what the comparison test tells us. All right, thank you.